It's time for doing something completely new. Chemistry. Cool. So basically, the hunt for projects and ideas and things and examples because I think that's kind of helping me see and get base ideas of of intuition bites that can be reused. And I think going through the basic textbook algorithms has helped me a lot to learn about the quantum Fourier transform, about phase estimation, about phase kickback effects, about search like amplitude amplification and all this kind of stuff that help you sort of. They are really cool building blocks for designing algorithms. And then I want to get into other areas that are touched by quantum computing right now where I can kind of get a grasp on what else can you do. And again, my knowledge in chemistry is close to zero, so I might really have a hard time here. But I want to sort of explore what other things out there. In Qiskit maybe as an example, right? But there's other things that I'll definitely explore. Because if you just let me just close all the stuff and show you how I got here. So if you go to here, you've got the section with notebooks and Qiskit tutorials. I haven't really gotten into Qiskit itself, but I think it's something that you don't really need to learn from scratch, and you can just, by looking at the notebooks, you'll probably get a fairly good grasp of what you can do with Qiskit and how the Qiskit works. I think that's not you shouldn't, if you're getting into quantum computing, don't learn Qiskit and don't learn any language. That's my recommendation. Just learn the whole abstract concept of circuits first, and then you'll figure out the language. That's kind of the easiest part. It's like programming. You don't just learn. You kind of start by using one language, and then you kind of easily learn how the other ones work as well. So it's kind of the same. So you've got finance, chemistry, and other stuff in here, artificial intelligence, which we've touched a little bit in the channel. So I wanted to kind of do an overview on what's within chemistry, see what's in there. I don't know. I haven't really checked it, so I'll just take a look at in the index. I'm assuming that's sort of the starting point. I just open here as well. Let me close that. See if we get somewhere. I really want to just give you like a 10 minutes or bird's eye view on this. Chemistry is a set of tools, algorithms, and software for use with quantum computers to carry out research and investigate how to take advantage of quantum computational power to solve chemistry problems. Cool. Qiskit chemistry translates chemistry-specific problem inputs into inputs for a quantum algorithm supplied by Qiskit Aqua, which then in turn uses Qiskit Terra for the actual quantum computation. Okay, so it seems like it's following the same approach, or the typical approach was like translate a problem into something that Qiskit Aqua can handle, and this may be one. I've heard about the VQE before, but I really don't know what it is, and maybe that's the algorithm they're talking about. How to declarative pragmatic approach. Let's take a look at declarative, and then let's open up the programmatic approach as well. Cancel. Oh my god, what have I done? Anyway, so declarative. Contributors. Okay. A shout out to the people working on this because I think it's super helpful. This notebook demonstrates how to use Qiskit chemistry to compute the ground state energy. Okay, so that's an introduction actually. Declarative approach. To compute the ground state energy of molecular hydrogen, H2, using variational quantum eigensolver. Okay, the variational quantum eigensolver. This is probably it's a bit complicated to navigate, What was the declarative approach? Oh, just what did it do? What happened? Can I just go back? Can I close this? Can I click on this? It just disappeared. No. Oh, sorry. I double clicked and I'm so stupid. Okay. I just probably should press. Oh. I hope I cannot touch. I hope I cannot mess up with any of these. That would be bad. Can I not just. How can I go back to view? Can I just go back to the view mode? I don't want to edit that. How can I run this? Run. Anyway. What? Come on. I got completely lost right now. Should I just log out and log in again? See what happens. Qiskit notebooks. Chemistry. Index. Declarative approach. Loading. So hopefully that works now. Yeah, looks like it works. So that dictionary, okay, so using the algorithm in the unitary coupled cluster singles and doubles variational form, which I have no idea what it means, this notebook uses the so-called declarative approach, a Python dictionary automatically generated via the Qiskit chemistry graphic interface, which summarizes the entire experiment declaratively. The dictionary is simply then passed as a parameter to the run method of the Qiskit chemistry solver to get the result of the experiment. Users who are more interested in learning the Qiskit Aqua and Qiskit chemistry APIs and or contributing new algorithm components can look at the same experiment executed programmatically. This notebook has been written to use the HDF5 chemistry driver. This driver uses molecular data that has been serialized from a prior computation. This allows this notebook to be executed with no additional driver installation requirements. Okay. So first we import the Qiskit chemistry, then we create a Python dictionary to specify the problem we want to solve. Okay. The first entry names chemistry driver, automatically set by default. Kubila optimized it with UCCSD variational form. VQE uses the variational method to find a minimum. VQE uses the variational method to find the minimum eigenvalue of a problem, which in this case is the ground state energy of the molecule. So you get state vector simulator. What? So this is the dictionary kind of for the parameters. Okay, so that's how you're parameterizing stuff. The driver. Okay, you probably need some deeper knowledge on what's the algorithm behind that. VQE might explore that. Now we can create a Qiskit chemistry object and call run. Okay. So see the FOC thing here? It's something that I saw when I was taking a look at Xanadu as well. This may take a short time and it will use a local quantum simulator to carry out the quantum computation that the VQE algorithm uses. So that's it. Okay, print ground state energy, result energy. That is the energy. Ground state energy, electronic ground state energy, computed part, frozen energy part. Well, our notebooks are documentation describing the various components. Okay, so I'll take note of these things to explore further. VQE is something to explore further that is relevant for the chemistry thing, seems like. What's the programmatic lead thing? I think it can also go here. So it seems it's based on so that's a programmatic approach. Define a molecule. We use the agent and STO3G basis with PySCF driver as an example. The molecule object records the information from the driver. Prepare qubit Hamiltonian. Here we set up the to be frozen and to be removed orbitals to reduce the problem size when we mapping to qubit Hamiltonian. That requires too much domain knowledge for me right now. But so that makes kind of no sense. Preferably, okay, for me to dive into this, but at least I get the VQE thing. It's an important thing to take a look at. That's kind of okay. That requires way too much domain knowledge. But the VQE algorithm is probably what I want to take a look at. Okay, and I think there's an actual notebook on these. Is it that all the chemistry related stuff is VQE, variational quantum eigensolver? So I'll probably just Google for that. Introduction. Maybe there is here. Fermionic Hamiltonians, molecules considered in this notebook and mapping to qubits, approximate universal quantum computing for quantum chemistry problems. It's pretty dense, people. Ooh. I'll probably look for something that's a bit more. So, introduction to VQE. See what we get. Oh, David Kopchak. I like it. That's the first result. Cool. That's probably going to be my next video. Okay, let's get into this. I like it. Like it. I like it. I like it. Cool. Chemistry, quantum chemistry. This seems to be the gist of it. I mean, this seems to be sort of a good first step, understanding what the variational quantum eigensolver is and how does this contribute and help with chemistry problems. Maybe there's something out of this that we can take in terms of intuition. Perfect. Cool. I mean, there doesn't seem to be anything else here, honestly. There is this community in chemistry, and maybe that's something that I'll take a look after that. Because I started like that a bit more. It's like getting really the hands-on actual code and actual problem solving, and I think that's going to definitely help me to understand more quantum computing in general. It's like the basics are good, but it feels like seeing examples helps you understand how to apply them and what you can do with this. I really don't know here where to start. README. I mean, I think that's because there are samples input files. Okay. Okay. There's a graphic user interface for Qiskit chemistry. It's kind of deprecated. Okay. Okay. I might even use that to get into Qiskit. Give you guys a first-hand experience in doing that. But let's focus on the VQE next time. Perfect. Cool.